Our final innovative talk will be given by Dr. Gilad Litvin, Chairman, Chief Medical Officer, and founder of CorNeat Vision. He will present his work on a new, completely synthetic keratoprosthesis.
Good morning, everyone. I'd like to thank Ed and the committee for this invitation. It's a privilege to speak before you today. These are my financial disclosures, and they are pertinent as I am the inventor and deeply involved in the development of the CorNeat Kpro, so take my things with a grain of salt. This is our first Kpro implantee, Jamal. He's a 78-year-old male. He has one functional eye, and that eye underwent 4 previous corneal transplantations, the last one about a decade ago, culminating in a cantamoeba infection, and this is pre-op on the table. We'll come back to Jamal. This is a device. This is the CorNeat Kpro. As you can see, it has 2 members, an optical component and a nanofabric integrating skirt, and a rim that fuses both of these elements together. Now you can see the device. It comes in a protective casing. The rim has 3 pairs of suturing holes, 4 bays for future access into the AC in case you need to perform surgeries, and grooves filled with a nanofabric to integrate the PMMA itself to the eye wall. A posterior undercut to house the remnant cornea, and flanges that assist the surgeon in inserting the cornea intraoperatively into that undercut. The nanofabric skirt is manufactured by electrospinning technology, and this technology allows us to create a non-woven matrix in the nanometer and micrometer scale. And you can see our ECM, artificial ECM with a strand of hair over it, and on the right-hand side, our Tenon's capsule collagen network, and you can see the similarities. Another differentiator is the fact that we anchor the device instead of in the corneal tissue like previous models, a tissue that's devoid of blood vessels and has very few cells. We anchor the device in the subconjunctival space, an area that heals vigorously. In order to test our assumptions, we shortlisted 4 configurations of this nanofabric and blinded ourselves to the configurations and tried initially to test them in vitro with human cells, with human fibroblasts, and afterwards validated our assumptions in vivo in a rabbit, and eventually found the winner that performed the best. That paved the way for extensive biocompatibility testing and an animal trial that was recently published in Cornea, you can see here, where we followed up 8 rabbits for 6 months. And this is the main finding of our animal trial. You can see the H&E slide on the left with abundant cell nuclei interspersed between the fibrils of the nanofabric skirt. And on the right-hand side with Mason trichrome, you can see collagen in purple and even a capillary coursing its way from one end of the skirt to the other. And this is again Jamal. I would like to thank Professor Irit Bahal for sharing this surgical video of the first in human ever implantation. So the procedure starts with a 360-degree peritomy, followed by epithelial debridement to avoid downgrowth, and then marking the center of the cornea. This is crucial to center the procedure on one central mark. You see Professor Bahal staining a marker tool and then stamping the eye, showing the surgeon where to lay the sutures, where the paracenthesis should be, and also the trephinations edge for a good visualization under the implant. Then she fills the eye with viscoelastic and starts placing the sutures first through the device and then through the corneal sclera where it is indicated. After the 3 safety sutures are positioned, she goes on to trephine the eye. She centers the trephine's crosshair again on that initial central mark, so the trephination will be centered on the undercut of the implant. After doing so, all that is left is to pull on the distal end of the sutures and approximate the device to the eye wall, sealing the eye and stopping the open sky segment of this procedure. After tying the suture, using a dedicated spatula called a snapper, she inserts the corneal remnant into the undercut, after which all that is left is to reposition the conjunctiva, suture it in place, and using T-seal, complete the procedure. You can see here in the rabbit, 1 month post-op, barely any inflammatory cell reaction. 2 months already cells have invaded into the matrix, and 6 months you have already seen complete collagenation of the skirt material. You can also see the anterior segment OCT of our patient with 4 months post-op, and the bottom picture showing the optic element in good positioning in the anterior segment, and the top hand picture you can see the skirt overlaid with the tenon and then the conjunctiva. To summarize our first-in-human experience, so far we have 2 implantees, Jamal, that you see on the top. He's almost 7 months post-op. He has a bad optical nerve, but still he sees 6/90. He's very, very pleased. He hasn't been able to see for a decade, as I was saying. And the second patient is an OCP patient who hasn't seen for 30 years. He's now 3 months post-op, and his vision is 6/9. The only thing that I want to mention is that both have shown some conjunctival retraction initially in the first few weeks that stopped once the tissue adhered to the skirt material and has been stable since. I think the conclusion, though, from my talk is not the artificial cornea, but the ability to integrate artificial, mechanical, and other components into our human body seamlessly with this technology, with this polymer ability, and I think it ushers a way to a new era of medical devices. I'd like to thank Professor Irit Bachal for being bold and performing this first-in-human implantation and being generous with her materials, and my team of 15, led by Mr. Almogale Raz, CorNeat CEO. All of them are very diligent and professional. I'd like to thank them, and thank you.
Thank you, very good. Ike, you've had some experience using this material in glaucoma surgery. Can you talk about it?
Yes, I had the privilege of being the first in the world to use the material as it biointegrates very well. It's a good, useful material to cover implants, for example, tube shunts. So far in our results, we've had excellent results. It's well tolerated. It's at a low profile. And, the biointegration, I think, is a real valuable asset. So in the glaucoma world, we've certainly seen, potential benefit here.
Do you have any sense that you have to have tenons available to make the integration of the capillaries? Because these patients are often, they have very sick eyes and maybe not have as much tenons.
I see the big difference between the rabbit trial and these initial patients. It's true. When you try and implant these in healthy young rabbits and you only lift the conjunctiva and the sclera is still with tenon, it's much simpler and it heals much better. These eyes are very scarred and the tenon and conj are fused together, so retraction is partly due to the tenon being retracted. And we're working on ways, perhaps we're thinking of doing Botox for the initial month in the extraocular muscles. These are only single-eyed patients usually to avoid the movement, because that might assist in or cause the retraction. And perhaps doing a relaxing incision only on the conjunctiva posteriorly in the fornix to allow mobility of the conjunctiva and lessen the tension. But it is a challenge. It is the challenge that we're facing now. But what we do see, and we saw in the rabbits, that even in areas where there is retraction, the skirt is filled with collagen and with fibroblasts and even capillaries, even in areas that the conj is not covering it. And there is no access into the anterior chamber. And this has been true for Jamal, 7 months post-op. The rim, about 1.5 millimeter, is not covered with conj, but his AC is quiet. And it doesn't seem like it's bothering him. And we cannot, of course, do any pathology to make sure that this skirt material in humans is full of cells and collagen, but we presume so.
Well, great work. I mean, obviously with these Kpros, tissue integration has been the main problem with a lot of these, we get extrusion, we get infections. I was wondering in terms of the intraocular pressure issue with these Kpros, and do you have now maybe a system? I heard Ike talking about another device where you're combining the two to maybe address that portion.
So we're working on Kpro 2.0, and we've contacted a Canadian company called Fizo. They do a fibro-optic measuring sensor for pressure, where you can embed it in the internal aspect of the PMMA lens, and with light and a membrane, you can gauge the pressure internally. Currently, what we do is we follow them with digital palpation, and every 3 months we do a serial OCT of the RNFL to make sure that nothing happens. And also, since for the first time this is a very wide aperture lens, the optical element is optical zone is 6.5 millimeters. We can also have the patient perform a visual field, so we can, except for the pressure, follow up a glaucoma patient like we would have otherwise clinically. And this is our solution now. Hopefully we will have in the next generation also an embedded pressure sensor.
Great. Well, thank you, Dr. Litvin. Very good work.
Thank you very much.